Hello everyone, welcome back to alkaline hydroxide 784, and today in the chemistry series we will be covering the chemical equilibria and equilibria. Yeah, I guess I said that correctly. Okay, can. um so as usual, we will be going through the learning outcomes, and yeah, there's nothing else really much to say. Okay, so the first one is explaining two different terms in terms of the rate of the forward and reverse reaction. So in a reversible reaction, which I guess is very familiar in the sense of the two arrow things, the one going towards the right and one going towards the left. That's how you recognize it as a reversible reaction. In this scenario, there is a forward reaction and a reverse reaction. So you would, of course, all reactions could be technically reversible reactions. It's just that the reverse reaction most of the time is super non-spontaneous, so it doesn't happen. But for the reversible reactions that actually do have a clear reversible reaction, it's usually because the reverse reaction is somewhat spontaneous or can happens easily enough for it to be visible. Okay, so yeah, so a reversible reaction is one that has both a forward and a reverse reaction, and both those reactions are somewhat spontaneous. And dynamic equilibrium is when the rate of both the forward and reverse reactions are equal. So yeah, like there is no change in concentration of the products. Both the reactions are going at the same rate, and therefore there's no change in concentrations of all of the things inside the reaction. So now we'll go to the main thing is usually asked about in this topic, which is Le Chatelier's principle. And actually, you don't really need to know how to pronounce this, so never mind. But the idea of this principle is that if there's a change to the system, like the conditions in the system, the reaction will adjust itself, the equilibrium will adjust such that to counteract whatever change affected it in the first place. So as we mentioned earlier, the term isn't just equilibrium but dynamic equilibrium in the first learning outcome. So in this scenario, dynamic really comes to play here, because it's not like there is no reaction going on. Both the reactions are definitely still happening. It's just that it's the same as when you visualize the idea of thermal gradients, right? From a hotter to a colder location, you've heard about the heat transfer between those two locations. And even at the equilibrated temperature, there is still heat transfer between both regions. It's just that the overall net transfer is zero. So likewise in dynamic equilibrium, the net change of the product concentrations are zero. But at the same time, this means that the reactions are still going on, and this can be seen very clearly when you disrupt the equilibrium. So the reactions will then increase or decrease their rates according to the disruption and try to go back to equilibrium. So if you were to first of all draw the rates normally, you would see that at initial conditions you would have each of the forward and reverse reactions having certain rates, and after a certain time, at time equilibrium, the rates will converge into one single line. And this is what we're going to use to describe the effects of Le Chatelier's principle, and see what happens when you change certain conditions. Okay, so first of all, the first thing that you can change is the concentration. So when you change a concentration of the stuff in the reaction, let's say maybe it's A becoming B, then you suddenly increase the amount of B. So like A is on the left and B is on the right. So B to A is the reverse reaction. So if you suddenly increase the concentration of B, it kind of ruins the equilibrium a bit because there's too much B in the system, and therefore there'll be a greater rate of the reverse reaction. So B to A will become faster, and how you would visualize that on the diagram that we are talking about is that in terms of the concentration of A and B, the rate is based on the gradient, right? So now that you change the concentration, the B's concentration will suddenly increase, and then the then what was I gonna say? Yeah, so B's concentration will increase, and that will be represented with the vertical line, as you can see, and A is still the same, and from there they will both try to come back to equilibrium, concentrations, and you see it by the way that I draw it. So first of all, the rate of the reverse reaction will increase, which will decrease the amount of B, and this will then be like a negative feedback loop. So since there is lesser B now, it's less likely to, like, the rate of increase of the reverse reaction will decrease, and until it comes back to equilibrium, a kind of equilibrium rate in a sense. Yeah, so that's how it works. So it's trying to counteract the increase in B by decreasing the amount of B. That's how it works. Yeah, so the position of equilibrium would be pushed towards the left, since we are looking at A being on the left. So we will now try to produce a bit more A in a sense. Okay, so then the next one is pressure or temperature change. So a pressure change means that you suddenly increase the pressure of both or the entire system, and temperature change will also have a similar effect of the entire system kind of change. But in pressure change, what happens is the concentration of both A and B will increase, because you imagine it like reducing the volume but having the same amount of stuff inside that volume. So yeah, the concentration will increase, and that would, in the A to B scenario, it doesn't really do much, doesn't really change the position of equilibrium. But if you have a scenario where it's something like 2A become B is the forward reaction, and B becoming 2A is the backwards reaction, then the reaction will favor, like, the favored reaction will be the one that helps to decrease the pressure, if let's say you're increasing the pressure. So in this scenario, if you increase the pressure, the concentrations will increase. And in order to decrease the pressure, you try to create lesser gas molecules. Yeah, so in this scenario, you're assuming that it is a gaseous system, because in a liquid system, I don't really think this is going to happen. In a gaseous system, it's more evident. So in order to decrease the pressure, the forward reaction will become faster, and therefore the position of equilibrium will shift towards the right. And likewise for temperature, it depends on a different thing this time, not really the number of molecules on either side of the equation, but more on the delta H, which we have heard about before. And in this scenario, the delta H of the forward reaction or the reverse reaction will then determine which reaction goes faster based on the temperature change. So let's say for our example, A becoming B is the forward reaction, and let's say that is an exothermic. Let's say A becoming B is exothermic, aka it releases heat. So it increases the temperature of the surroundings. So when you increase the temperature, you do not want to increase the temperature of the surroundings again, right? So the reverse reaction, which is endothermic, will then be favored in order to decrease the temperature of the surroundings, and vice versa in the sense. So just use that to figure out which one is favored in the sense. So that's how you describe your shifting of the position of equilibrium. And Yes, that's for learning outcome B. For the next one, we would look at the other kinds of a different kind of thing that could be affected by these changes, which is the equilibrium constant. And the equilibrium constant is, well, well, how you would write it out would be the Kc or the Kp. And that's actually the next one, so but I'll cover that first because otherwise you don't really it doesn't really make sense to say this without saying that. So in order to write down the Kc or the Kp, a concentration will be based on maybe liquid systems or even gaseous systems if you know the concentrations, and pressure is mostly just gaseous systems. So for Kc, you would be writing the concentrations of the products, the, the product of the concentration of the products, and over the concentration, the product of the concentration of the reactants. So in this case, we are referring to a forward reaction. So let's say in the A to B, our Kc would be concentration of B or concentration of A. Yeah, so for Kp, we are looking at partial pressure, because partial pressure is pretty much like concentration. It's just, yeah, you know what partial pressure is, so you can do that similarly. In our A to B scenario, you would be writing it as partial pressure of B or partial pressure of A. And when you have more than one, like the coefficient is not 1, in our 2A becoming B scenario, then our Kp would instead be partial pressure of B or partial pressure of A squared. And this will apply for concentration as well. So if you were to write it in concentration, you get concentration of B or concentration of A squared. And yeah, that's how you write the equilibrium constant and the expression in a sense. Okay, and from there you have to deduce the units. If there's a square, then your unit will be different in a sense. If it's equally cancelled out, it has no units. But if there is a square or a cube even in one of the on either the denominator or the numerator, then you will get a certain unit out of it based on the concentration or partial pressure. Okay, so from here we can decide, okay, so let's say the change in concentration, pressure, temperature, catalyst, whether these things affect the value of this equilibrium constant. So the equilibrium constant can also be defined by the rate of the forward reaction or the rate of the reverse reaction. And you're wondering, wait, why does this relate to whatever we just discussed for the expression? Well, the reason is because the rate is the first and foremost definition of the constant, and this can be derived from that definition. So let's say you start with Kc is equals to rate of forward reaction or rate of reverse reaction, and then the rate of forward reaction is the small k concentration of A. uh hmm okay, wait. Yeah, it's rate of forward reaction or rate of backward reaction, then why, I don't know. Okay. Or rate of the backward reaction, and then from there you will get your concentration. Okay, so the idea is that yeah, so you get the idea lah. So if you were to change concentration, that will definitely change the what is it they'll definitely change certain things. Depends on which concentration you're changing, because you do realize that the oh, okay, actually do not use the rate equation to derive this thing, because this is depending on a different logic. So please don't use the forward or rate or backwards rate to get the Kc and the Kp and all that. Okay, so now we will move on to how the changes in various things affect this. Okay, so a change in concentration, if you look at the Kc and Kp, obviously the change in concentration slash partial pressure or something is kind of going to affect the Kc and the Kp in a way. Or is it? Because this is at equilibrium. So when you change the concentration, the concentration, that the value of the, like if you try to calculate Kc or Kp with those values, they will not be the equilibrium one. It will be represented by something else, Q, like I think you use a Q or something. So Qc, and this is not equals to Kc. So the actual Kc isn't affected by the changes in concentration because eventually the system will go back to equilibrium, and even if the numbers are slightly different, the ratio will be the same and the Kc will be the same. Therefore Kc isn't affected by concentration. So pressure or temperature. Okay, so when it comes to pressure, if you are changing the overall pressure, then the Kp will not be affected because the pressure of all of the reactants will be affected at the same time, so it doesn't actually change the Kp either. So in temperature, when it comes to temperature, it can affect the Kc or Kp because it's temperature. Yeah. So the idea behind it is that the temperature will change the actual rate of reaction. So like the temperature will affect the actual rate of the forward or reverse reaction at equilibrium. And therefore the Kc and Kp will change if you change the temperature. And the presence of a catalyst, is you may think it will change the Kc or the Kp, but it actually doesn't, because most of the time the catalyst will increase the rates of both the forward and reverse reaction to an equal proportion, and therefore the overall ratio will still be the same. And therefore it doesn't actually affect the value. So all of these changes, the only thing that affects the equilibrium constant is temperature. But everything will have a role in Le Chatelier's principle, except for the catalyst maybe, I guess, because that's not very relevant. Okay, so okay, so let's move on to the one that's after, like the next one that we haven't covered yet. So calculate the value of the equilibrium constant. So we have the expression already, right? So you just use the data in the question and you can just put it in. You have to make sure the value that's there is of the equilibrium value. You shouldn't be using the initial conditions or anything, but you should use the values of concentration or partial pressure from at the equilibrium state. Yeah, so that's pretty important, and you shouldn't accidentally use the wrong concentration. Yeah, so just use a calculator, type in the numbers, and hopefully you don't make any careless mistakes and you can get the value pretty easily from the equilibrium concentration or equilibrium partial pressure. Okay, so the next one is, if you do not know the equilibrium concentration but you have other data like the Kc data and maybe the initial conditions, you would want to try to find out what's the concentration at equilibrium. So how do you do that? Well, if you can do it there's this small caveat here, which is that of course it says such calculations will not require the solving of quadratic equations, but it is possible to make it into a quadratic equation if you so wish to. Yeah, it's up to you to decide whether you want to do that or not, but you can do it or you can choose not to, and I'll tell you how in a second. So how you should start doing it, first of all, is to imagine the change in concentration at equilibrium as S or something. You call it S maybe. And then let's say you have a 2 or 3 as a coefficient, then you must make sure the change is 2S, 3S according to the coefficient that you have. And after you see what are the changes, like for example, you have to first think of what we start with. Maybe we have A first. like a certain amount of A and not a lot of B, and therefore you would imagine A is the one decreasing and B is the one increasing in concentration. So for A to B, for example, you would say A minus S, and then B, and for the B you would be B plus S. So after that you translate this into a Kc expression. So at equilibrium the concentration is B, original concentration of B minus S over the original concentration of A minus, sorry, or original concentration of B plus S or the original concentration of A minus S. So under in certain circumstances you can just use this to calculate what the S is and then get the answer. But under certain situations, if one of them is in great excess, then you would ignore the change in S for that particular one and only have one to solve, I think, and from there you can get your S pretty easily without having to really do any quadratic equation. But if you choose to keep all of the S's, you may have to deal with a quadratic equation. Yeah, and you can just use a calculator to solve it. You don't need to do your actual algebra stuff. Just use a calculator, type in all the values, and you'll be fine. Yeah, it's pretty easy to do. Okay, so the next one is to show understanding that the position of equilibrium is dependent on delta G standard. Yeah, the standard delta G. So what this means is, at the very beginning I was talking about the spontaneity of the reactions. In this scenario you would be looking at the overall delta G of the entire thing, and if you realize that the delta G is very negative, then it's very likely that the reaction will go to completion or is all very close to completion. Yeah, so if you're looking at delta G very negative, reaction is more likely to go to completion. The delta G is very positive. You're looking at a forward reaction per se, then the reaction is very likely to not happen or the reverse reaction is more likely to happen. And if delta G is very close to 0 or between 1 and -1, around there, I think not really 1 and -1, more like 0.1 and -0.1, I don't know. If it's in that range, then it is very likely to have a reversible reaction. Yeah, so that's the idea of delta G in a way. But the more negative or positive delta G is, the more the position of equilibrium shifts to the right and the left and things like that. So delta G positive means it will shift more to the left. Delta G negative means it will shift more to the right, and delta G very close to 0 will be right in the center at equilibrium state. Yeah. So the final learning outcome, which is about the Haber process, I probably do not know how to pronounce this, but you know what I'm talking about. Yeah. So I'm gonna explain the conditions along with the explanation of equilibrium in a sense. So for that, I'm gonna refer to a website, which I'll put the link to below. And in this website, which is the Chem guide thingy, yeah, you can just see the link below and then look at it yourself. I'm gonna follow the conditions that they've written here. Okay, so for the Haber process in an industrial setting, you combine nitrogen and hydrogen gas, 1/3 volume, and you use the conditions of 400 to 450 degrees Celsius at 200 atm with iron catalyst, and afterwards you cool everything, all the products, like the resultant stuff, you cool it and try to remove as much ammonia as possible, and then you return the rest of the gases back into the reaction. So that's how the cycle works. So if you're unaware of the process, like the equation for this is nitrogen plus 3 hydrogen becomes ammonia, and ammonia can go back to these two constituents as well. And the delta H for the forward reaction is negative 92 kilojoules per mole. So it is exothermic actually. So how do you drive the reaction to produce more ammonia and not end up with your reactants rather than your product? So that's the main question that the industry tries to solve using these conditions that we just saw. And the first condition obviously is the temperature, the 400 to 450 degrees Celsius. So the 400 to 450 degrees Celsius is quite hot, but it's not too hot until the gases end up, I don't know, doing some other reaction. So at this temperature, the reaction is somewhat controlled. I think it's like not too fast and not too slow as well. And it also helps to push the wait, actually what was I trying to do? Oh yeah. So wait. Yeah, so the reason why the temperature is 400 and 450 is because they want to increase the rates of the reaction a bit more. So the temperature itself will increase the rates of both the forward and the back in the reverse reactions. But the reason why they do not want to increase it beyond 450 is because we saw the delta H is exothermic. So if you increase the temperature too much, then the reverse reaction will be favored. And that is not favorable for the industry. So that's why the temperature is technically of a moderate amount. I mean, this may not seem moderate to a normal person, but in the industry, this is actually moderate temperature. Okay, so for the pressure, it is also of a moderate pressure. Even though this may not seem like moderate pressure to you, it is considered moderate pressure of 200 atm. And that is because if you look at the whole reaction again, it's like 4 moles of gas becoming 2 moles of gas. So the reaction actually becomes like decreases the pressure. The forward reaction decreases the pressure of the reaction. So the pressure technically helps in a sense, and therefore you actually need this decently moderate moderate pressure, which is 200 atm, but you cannot go too high of a pressure because it is not safe to do so. So the pressure is way higher than normal atmospheric pressure, and this allows the reaction to be pushed forward, like the position of equilibrium goes towards ammonia. But at the same time, it is not so high that the company or the industry cannot manage the whole reaction in the sense. Yeah, that's why the pressure is at 200 atm. And the third one is the ion catalyst, and the reason why a catalyst is used is to increase the rates of the reaction. Of course, the rate of both forward and reverse reactions will be increased, but the point is just to increase the rate. It's like why they have the temperature at 400 is the same reason for that as that in the sense. Okay, so you might be wondering, okay, so two of them increase the rates of both the forward and backwards reaction. So how do you make sure to favor the forward reaction more than the backward reaction? Simple, just remove the product. Yeah, that's pretty much what one of the important steps is here, which is to cool the gases afterwards and return the unreacted gases back. So this has two consequences. The first thing is to remove as much ammonia as possible from the reaction mixture by liquefying it, while the other two gases will not be liquefied because ammonia has, well, a much higher boiling point than these two, so it'll become a liquid first before hydrogen or nitrogen ever becomes a liquid. So the liquid ammonia can then be funneled off and used, and that's a product that you need in a sense. So it also helps to drive the reaction forward because when you decrease the concentration of ammonia, the reaction will want to push the position of equilibrium towards the right. So yeah, that's the point of it. And when you return the rest of the gases back into the whole thing, it also increases the concentration of nitrogen and hydrogen, which also tends to push the whole thing towards the right. So this whole process is pretty efficient just because, you know, you are trying all the ways to push the position of equilibrium towards the right, apart from the temperature and the catalyst bit, which is more of just increasing the rate of reactions that you don't take forever to produce ammonia. Yeah, that's their purpose in a sense. So hopefully that helps. I think oh yeah, the another important thing to take note is the original infusion of nitrogen and hydrogen is in stoichiometric ratios. So nitrogen is like 1 and hydrogen got 3. And the reason why is because this helps to favor reaction and doesn't have like unwanted extra molecules hanging around. So the reaction is more efficient when it's done that way in the Haber process. It may not be the same for all reactions, but for this definitely works very well for it. Okay, so yeah, that's the final one, and I hope that actually is a bit more insightful way of looking at the Haber process rather than just, you know, staring at it in your notes. And I hope you understood the reasons behind the conditions in the Haber process. So this topic is actually quite important to the industry in general, like the chemistry, the like chemical engineering, or like the chemical production industry in a sense. Yeah, so if you're into this kind of things, you can choose to learn about it in the future, I guess. I don't know. Anyways, I hope you found this video useful, either because, I don't know, in case you're at home and you don't really want to go to your school and you just need a different way to learn about it, then yeah, I hope this video helps. Yeah, if you did find it useful, please press the like button and subscribe. And with that, I would like to say thank you and bye.